In this video, we'll look at the pre-calculus algebra topic of linear and absolute value inequalities. We're going to probably focus most of the time on the absolute value inequalities. That tends to be the most challenging. Now, this is a fun example. Are you in love? As years go by in a relationship, three key components of love, passion, commitment, intimacy, progress differently over time. Passion peaks earlier in a relationship and then declines, and by contrast, intimacy and commitment build gradually. When you look at the examples in our textbook, not in this video, but in our textbook, you should find some applications where we use mathematics to explore relationships among these three variables of love. So if you were not thinking about doing your homework, I hope that inspires you to jump in and do it. So do the homework. Let's look at a quick review topic here. We've got some symbols, an intersection symbol and a union symbol. So this first symbol is called an intersection, and it's called intersection, and you could replace, when you're reading a statement of symbols with that intersection, you could replace the intersection with the word and. Do you see this mnemonic I'm trying to lead you towards? You might remember that the and kind of looks like that intersection symbol, right? The first letter of, letter of the word and. Here's an example. Down below I have a Venn diagram, and in this Venn diagram, it's called a Venn diagram. And I could use this Venn diagram to look at the intersection of A and B. A and B means give us everything that's in both set A, that's the purple set, and set B, everything that's in both. The only thing that's in both is that rectangle, the blue rectangle. So the shape that's in both is the blue rectangle. On the contrary, so comparing to that, we've got this union symbol. It looks like a U, and notice the U in the word union, that's a mnemonic. That's how you might remember which one is a union, which is an intersection. And for a union, we could replace it with the word or. So when I look at the Venn diagram below, anything that's in A or B would be all the shapes that are in either set A or in set B. And by the way, it's going to include that shape that's in both. So it'd be this circle, triangle, rectangle, and the star. All of the shapes are in one or the other. I hope that short review helps you remember what an intersection and union are, and their key word, or for union and for intersection. That's going to come into some examples here. So when we look at this, express 1 to 6 in set builder notation and a graph. I'm going to start with the graph. So if I were to graph the set from 1 to 6, I recommend an alternate color. So from 1 to 6, I could see that that's everything that's all the x's that are greater than 1 and also less than or equal to 6. If I put that together, I could say the x's are sandwiched between the 1, so the x's are greater than 1. When I read this backwards, right? X is greater than 1. And the positive 6. So all the x's that are sandwiched between a 1 and a 6. Do you remember that for the bracket, I've got to say or equal to? One mnemonic for that is you see that line. Let me erase it here. You see this line in that bracket, right? So that's one way to remember that that's the or equal to. Express this set -3, including -3, up to infinity. Again, I'll start with a number line, a graph. We're going to go from -3 up to infinity. And it looks like we're going to include the -3, right? So from -3 up to positive infinity, it looks like that's all the x's that are greater or equal to -3. Now going back to put these in set builder notation, remember it looks like this. The set of all x's such that 1 is less than x is less than or equal to 6. Or the set of all x's such that x is greater than or equal to -3. I hope that that example helps you. If you need further assistance with this, please ask. Use a graph to find these sets. We want everything that's from -3 to 0, and there's that intersection. And, ooh, did you see what I've done here? Close your eyes and ignore this for just a minute. I pre-wrote these, and I wrote them with the incorrect word on there. I'm not sure how I did that, but they should look like this. Okay, let's go forward with this, the and, intersection and. Here's how we could approach this. I'm going to draw the number line for the -3 to 0 and match it up to the -1 to 2. So I'm going to put all of the numbers on both number lines. You see how I've done that? I'm going to start with the -3 to 0. -3 to 0 would start at -3 and end at 0. The -1 to 2 includes -1 and goes up to 2. If I wanted everything that was both pink and blue, I'm going to get everything from -1, including -1, up to 0. Let me show you this here. If I wanted what was in both, I could go from this -1 up to 0. -1 to 0. Notice that the -1 is included. It's both in the pink and the blue. But the 0 is not included in the pink. We stop at the 0. Let's try another one. -3, 0. For this one, I'm going to try showing this on one number line. But if we went from -3 to 0, excluding both the -3 and the 0, or -1 to 2, including the -1 and the 2. This or means anything that's pink or blue. It might be one of the two, or it might be both. And you see that that's going to be this -3 all the way up to the 2. And that's the set -3 to 2, excluding the -3, including the 2. Solve and graph the solution set on a number line. I'm going to start by solving the inequality. So I'm going to divide both sides by -9. But do you remember that when we divide by a negative, this inequality changes its direction? So it was less than or equal to. Now it's when I divide by a negative, I've got to flip it around. You treat an inequality the same as an equation, except that when we multiply or divide by a negative, it flips. So this would give us that x is greater or equal to -4. I could put that on a number line. I'm going to draw the -4 in at least one number before and after. Everything that's greater or equal to -4 would start at -4 and go up to infinity. So in interval notation, I'd say -4, comma, infinity. Oh, wait, greater than -4. So -4, comma, infinity. Let's look at number 3b. X minus 4 minus 3/2. I think this was supposed to say less than or equal to x over 2 plus 1. I'm going to start by multiplying everything by 4, just so I can get rid of those fractions. When I do that, I have 4x divided by 4 is x. 3/2 times 4, the 4 and the 2 would reduce, so 4 divided by 2 is 2. 2 times -3 is -6. Less than or equal to 4x over 2. 4x divided by 2 is 2x plus 4. Now off to the side, let me show you what I just did, just in case that was too much at once. I took this 4 and multiplied it by everything. So here the 4 is divided out, and we're left with x. 12 divided by 4 is 6. 2 times 3. 2 goes into 4 twice. And then 1 times 4 is 4. Next, I'm going to subtract 2x from both sides, so I can isolate the x. X minus 2x is going to be the opposite of x. And then I can add 6 to both sides. And that's going to give me -x, the opposite of x, is less than or equal to 10. So x is greater or equal to the opposite of 10, because I'm going to multiply by a -1. When I multiply by a -1, that inequality has to switch directions. Now, if I want to show all the x's that are greater than or equal to -10 on a number line, it might look like this. I'm going to start at the -10, include the -10. and go in the direction of that arrow. So that would be -10 included up to infinity. And we always have a parenthesis on infinity because you can't actually equal infinity. Number 3C, here's an interesting example. We've got an elevator at a construction site, and we've got a maximum capacity of 3,000 pounds. The operator is 245 pounds. Each bag of cement is 95 pounds. And because he doesn't want to plummet to his death, he is going to, he or she, the construction worker, the elevator operator, is going to decide how many bags of cement can they include. So we've got the operator's weight of 245 plus the cement weight, 95 times each bag. Notice that that has to be less than or equal to the 3,000. But the very most we can have is 3,000 pounds of weight. So if we solve this inequality, subtract 245 from both sides, 3,000 divided by 200, or minus 245 is 2,755. And then divide both sides by 95. And I'd get that x is less than or equal to 29. What does that mean? Therefore, you may have up to 29 bags, or 29 bags at most, because we let x equal the number of cement bags. Right? This x was a number of cement bags. All right, let's look at another type of example. A problem where we solve a compound inequality. You know what we're going to do here is we're going to look at the x in the middle here and think of what would I do to isolate that x. And whatever I do, I'm just going to do it to all three pieces of the inequality. So for example, I'm going to add 1 to cancel out that -1, right? So when I add 1 to the middle, I'm going to add 1 to both sides. -11 plus 1 is -11, less than 2x, less than or equal to -5 plus 1 is -4. And now I'm going to divide both, or all three pieces, by 2. Because I'm dividing by a positive value, I don't have to flip it around. So it's just the -11, plus 1. I didn't write the plus 1, did I? -11 plus 1 would be -10. I don't know if I wrote that and it just didn't pick it up or what. But -5 plus 1 is the -4. When I divide this, it's going to divide evenly. -10 divided by 2 is -5. Less than 2 divided by 2 just leaves me x. Less than or equal to -2. It was okay that I had a negative already there. What I'm dividing by, the blue here, is dividing by a 2. So when I divide by a positive, I don't have to flip the sign over. When I write this in interval notation, the answer is going to be all the x's that are between -5 and -2. Notice that -5 has a parenthesis because it's less than, but the -2 has a bracket because it's or equal to. Just a couple more examples, but these last examples are going to be absolute value inequalities. So I'm going to continue that in the next video so that we can take a break. Inequalities. So that we could take a short break here and you could review the last video before you watch this last part, just 3 more examples.